Hello and welcome back. In this video, we'll begin with finishing the problem that we started last time. We were given this inequality, 2x squared is less than or equal to minus 6x minus 1. We first moved everything to one side so that we had our inequality as with a 0 on one side, which makes it a little bit easier to come up with. The first step in solving an inequality is always this, but the simplest way to do this is to divide the domain up into different regions, and those regions are going to be separated by the solutions to when our polynomial is equal to 0. So we found that the roots of this polynomial were not very nice to look at, but negative 3 halves minus square root of 7 over 2, and negative 3 halves plus the square root of 7 over 2. So what we need to do now is test a point in each one of these regions. We will need to see whether or not this half of the polynomial is going to be greater than 0 or less than 0 to the left of our intercept, in between our intercepts, or to the right of the intercept. So we'll just pick a point in between each one of these and test it. So for instance, here, if we want to pick a number that's less than this, negative 3 halves is about negative 1.5. Negative square root of 7 over 2 is about negative 1.5. So a number that's less than this would be maybe negative 10. A number in between these two, well, this is negative 3 halves minus a little bit. This is negative 3 halves plus a little bit. So negative 3 halves is certainly going to be a number in between here. And then this last one, 0, for instance. Oops, I wrote this interval down wrong. This should be all of the numbers greater than this boundary point right there. So 0, for instance, is going to be to the right of that point. So let's test each of these. So we plug it up into our polynomial on the left-hand side. So this is going to be 2 times negative 10 squared plus 6 times negative 10 plus 1. 2 times negative 10 squared. Negative 10 squared is 100. So this is going to be 200 minus 60 plus 1. 200 minus 60 is 140 plus 1. Well, that's 141, which is certainly positive. So over here to the right, we are going to be positive. In between, if I plug in negative 3 halves, 2 times negative 3 halves squared plus, let's see here, 6 times negative 3 halves plus 1. And what do we get? Negative 3 halves squared, well, on the top of the fraction we'll have 9, and on the bottom of the fraction we'll have 4, but I can cancel the 2 out. So this will be 9 halves. If I multiply this, the 2 and part of the 6 will cancel, so this will be minus 9 and plus 1. So if I think about this, 9 halves, 9 is the same thing as 18 halves. So 9 halves minus 18 halves is negative 9 halves. Plus another 2 halves is going to be negative 7 halves. Again, this is something that you can go through and check those details a little bit slower. This is going to be less than 0 in between here. And then our last region, 0, if I plug this in, 2 times 0 squared plus 6 times 0 plus 1, well, anything times 0 is 0, anything times 0 is 0, and if I add 1 to it, well, that's just going to be 1, which is greater than 0. So ultimately, I know in each one of these regions whether or not our polynomial is going to be positive or negative. So when is the function going to be less than or equal to 0? So my answer in between this region is the only place where my function is less than 0. So between negative 3 halves minus the square root of 7 over 2 and negative 3 halves plus the square root of 7 over 2. But it's or equal to, meaning that when my function is equal to 0, that should be included in the answer. So I will use square brackets. Maybe I'll use red to highlight this. So my answer will be the interval from negative 3 halves minus square root of 7 over 2 to negative 3 halves plus the square root of 7 over 2, including the endpoints. So I use square brackets. Let's do one final example with a polynomial inequality. So we have x cubed plus 3x squared is less than or equal to x plus 3. So again, first thing we want to do is put everything on one side. So we'll keep the left-hand side the same. I'll move the x over by subtracting an x from both sides. And I'll move the 3 over by subtracting a 3 from both sides. Oops. And what I'm left with is just 0 on the right. So again, I want to solve when is this equal to 0 to split it up into the different regions that I'll need to check. This question from the book is nice because we can factor this a little bit. So what I'll do is I'll split this up into the first two terms. So I can pull an x squared out of the first two terms. And I'll be left with an x out of there and a 3 out of there. And what you'll notice is that back here, I can also see an x and a 3, but after I pull out a negative 1. So far so good. I pull an x squared out of the first two terms, a minus 1 out of the second two terms, and now I have an x plus 3, and I can pull that out. So I have x squared minus 1 times x plus 3. So again, I just pulled an x plus 3 out of both of these. And an x squared minus 1, this is again, I can factor this. This is going to be x minus 1, x plus 1. Because this is x squared minus 1 squared. And then we have that last factor. So again, we can solve for when this is equal to 0. The only way that three numbers can multiply together to get 0 is when at least one of those is equal to 0. So we have x minus 1 is equal to 0, or x plus 1 is equal to 0, or x plus 3 is equal to 0. And in each case, I can solve that. X is equal to 1, or x is equal to minus 1, or x is equal to negative 3. So on our number line, if I have 0, our boundary points where our x-intercepts are going to be at 1, negative 1, and negative 3. Excuse me. So I'll have 4 regions to look at this time. I'll have the region to the left of negative 3, in between negative 3 and negative 1, in between negative 1 and 1, and to the right of negative 1. So let's split these regions up. We have the region to the left of negative 3. We have the region in between negative 3 and negative 1. We have the region between negative 1 and 1. And we have the region to the right of 1. So we'll pick a test value from each one. So a number less than negative 3, we can plug negative 4 in. A number between negative 3 and negative 1, negative 2 works. A number between negative 1 and 1, 0. And a number between 1 and infinity. Let's use 2. So again, if I plug negative 4 into my expression, we'll have negative 4 cubed plus 3 times negative 4 squared minus a negative 4 minus 3. Negative 4 cubed is going to be negative 64. Negative 4 squared is 16 times 3 is 48. Minus a negative 4, well that's plus 4. and we have a minus 3. So 64, negative 64 plus 48 is 16. Plus 4 is negative 12. Minus 15, well, that's negative 15. Oops. Which is certainly negative. So to the left here is going to be negative numbers. In between negative 3 and negative 1, I had negative 2. So let's try this. Negative 2 cubed plus 3 times negative 2 squared minus a negative 2 minus 3. Negative 2 cubed is negative 8. Negative 2 squared is 4 times 3 is 12. Minus a negative 2, well, that's the same thing as plus 2, minus 3. Negative 8 plus 12 is 4, plus 2 is 6, minus 3 is 3. So we jump from being negative to positive. At 0, well, this should be fairly straightforward. 0 cubed plus 3 times 0 squared minus 0 minus 3. Well, that's 0 plus 0 minus 0 minus 3, which is just negative 3. So we're going to be negative in this region. And then the last one, 2. All right, 2 cubed plus 3 times 2 squared minus 2 minus 3. 2 cubed is 8. Plus 3 times 2 times 2 is 12. Minus 2 minus 3. My face is in the way. This will be 8. 12 is 20. Minus 2 is 18. Minus 3 is 15. So we are again positive. I wrote the same thing I want is positive. There we go. This makes more sense. So we go from negative to positive to negative to positive. And there we have it. So we want to know when is our function less than or equal to 0. So it's less than 0 in this region and less than 0 in this region. But because it's or equal to, we'll need to include the places that our function was equal to 0. So our answer, we have to include the region to the left of negative 3, so negative infinity up to negative 3. But we have to include negative 3 because that's when our function was equal to 0. And then we also have the region between negative 1 and 1. But we have to include negative 1, and we have to include 1 because it could be equal to 0 as well. And those were our solutions. And to put those together, we will take the union. Again, I'll put this in red so it stands out a little bit more. Okay, so we'll stop there. In the next video, we'll do the final thing in the chapter, which is to look at what happens when you have rational functions and not just polynomials.